Every day you open your favorite app, you scroll, you pause, you click, and somehow the next video feels perfectly chosen. It's not luck, it's not magic, it's mathematics operating at planetary scale. Today we're going beyond the interface, beyond the thumbnails, beyond the UI animations, and into the mathematical engine quietly shaping your digital reality. We strip away the interface to expose the stochastic gradient descent and matrix factorization driving every recommendation. We trace how weighted vectors transform human behavior into cold, predictive geometry. By dissecting the latent space where preference meets probability, we reveal the mathematical machinery quietly engineering the modern flow of global information. Every time you open apps like YouTube, Instagram, or TikTok, you are not browsing content, you are entering a probability engine. At its core, a recommendation system solves a ranking problem. Out of millions of possible videos, it chooses which ones maximize the probability that I will click, watch, like, share, or stay. Mathematically, it begins with data, as each interaction like clicks, watch time, scroll speed, and pauses is encoded as numerical features. You become a high-dimensional vector. Each video becomes another vector in the same feature space. Now the system needs a similarity measure. Often this similarity starts with dot products or cosine similarity. If the vector aligns strongly with a video's vector, the score increases. Geometry becomes behavior. But raw similarity isn't enough. Platforms use matrix factorization, the same idea that powered early recommendation systems like the Netflix Prize era. Imagine a giant matrix where rows are users, columns are videos, and entries represent engagement. Most of this matrix is empty. Matrix factorization decomposes it into two lower dimensional matrices, user latent factors crossed with item latent factors. These latent factors represent hidden dimensions like comedy preference, political leaning, editing style tolerance, and niche interests without ever explicitly labeling them. The algorithm doesn't know you like astrophysics documentaries. It just learns that your vector aligns with others who do. Training this system requires optimization, like the stochastic gradient descent. The model predict engagement probability. Then it compares prediction to reality using a loss function, often cross-entropy for classification or mean squared error for regression. SGD computes gradients of this loss with respect to millions or billions of parameters and nudges them in the direction that reduces error. This process repeats millions of times per day. Over time, the system reshapes the latent space so that similar behaviors cluster together. This embedding space becomes a map of human preference. Viral content is not random. It occupies dense regions of high engagement probability. Modern systems go beyond matrix factorization, ingesting thousands of features like device type, session duration, time of day, trending velocity, and predicted future watch time. Architectures often include embedding layers, multi-layer perceptrons, wide and deep models, and reinforcement learning for long-term engagement optimization. In reinforcement learning setups, the platform is not just predicting the next click, it is optimizing a reward function over sequences of interactions. Your feed becomes a dynamic control system. And here's the critical insight: the objective function defines reality. If the loss function prioritizes watch time, the system amplifies content that maximizes watch time. If it prioritizes comments, it may favor controversy. The math doesn't have intent, but the objective does. This creates feedback loops. My behavior updates the model updates my feed. The feed updates my behavior. Over billions of users, this becomes a planetary scale optimization problem, one that subtly shapes public discourse, culture, and attention economics. So the next time your feed feels uncannily accurate, remember, it's not intuition. It's linear algebra, probability theory, and gradient descent. quietly mapping human curiosity into predictive geometry. And that geometry is constantly learning you.